next speaker is Professor B R Mehta from Indian Institute of Technology, Delhi. His talk is going to be on size-selected rare earth and palladium nanoparticles for hydrogen-induced switching and sensing devices. Dr. Mehta is a professor of physics at Indian Institute of Technology. He is the principal coordinator of the Nanoscience and Technology core group under the Nanoscience and Technology Initiative of the Department of Science and Technology at IIT Delhi. His specialization in the experimental solid-state physics and material science, nanoscience and technology. His areas of interest are nanostructured materials and thin films, interaction of gas molecules with nanoparticles and nanoparticle-based gas sensors and switchable devices, and also on rare earth metal and palladium nanoparticle structures, wide band gap and bipolar conductivity oxides, scanning probe microscopy and high resolution electron microscopy and nanotechnology education. His areas of research are synthesis of nanoparticles and nanorods, structures of sensors, switchable materials, light emitting and photovoltaic applications. I request Prof. Mehta to give his presentation.
Good evening. I think I'm B R Mehta from, this is my institute, Indian Institute of Technology, Delhi, at New Delhi. And I'd just like to give a small brief introduction about various other activities related to nanoscience and technology at our institute, and then I will move on with my lecture. In our institute, we have the activities on nanoscience and nanotechnology under two programs. One, we have what is called a institute thrust area. Our institute, IIT itself, has declared some 5 thrust areas. And in these thrust areas, the institute has provided a lot of funds and other facilities for carrying out this work. And also our Department of Science and Technology, Government of India, under its Nano Mission program, have around 11 units on nanoscience in India. And one such unit is at IIT Delhi, and the title of this unit or the focus of this unit is on nanostructured materials, synthesis, simulation, and application. And so a large number of departments, I think right now there are around 17 departments and centers, which are faculty members from these different centers are carrying out research in the areas related to nanostructured materials. But the major participating departments, especially in the beginning, were Department of Physics, Chemistry, Textile Technology, Biomedical Engineering, and many other departments. And the main goals of this unit on nanoscience is to carry out interdisciplinary research in nanostructured materials and establish characterization facilities, especially suitable for nanoscience and nanotechnology, and also to have educational teaching program in nanoscience and nanotechnology. So these are in fact some of my research areas in which I am actively participating. The first area is rare earth nanoparticles for hydrogen-induced switchable mirrors, palladium-hydrogen interaction in thin films, nanoparticles and size-selected nanoparticles, cadmium sulfide, cadmium telluride, and carbon nanotube composite and quantum dot solid cells, synthesis of size-selected nanoparticles, and oxide thin films and nanorod structures for resistive random access memory applications. So in this talk, what I will be covering these 3 areas which are there in the blue, and my main goal in this talk is to take you from the conventional materials, these rare earths and palladium materials, and oxide and dioxide materials. These are 2 or 3 classes of materials which I will be discussing about. And around 10 years back, thin films of these materials were being utilized for what is called switchable and sensing devices and resistive random access memory devices. And what I'm going to show you is that how, starting with thin films, we move on to nanocrystalline films. You decrease the crystallite size of the films, bring the crystallite size to nanometer region. How does one change the properties of these materials when we move on from thin films to nanocrystalline films? And then we go on to what is called size-selected nanoparticles. In the size-selected nanoparticles are important because from material science point of view, why one is interested in making nanomaterial is you can change the properties of materials by controlling dimensions. And hence size distribution is very important. It's very easy to make nanomaterials or nanostructured materials, but it's extremely difficult and challenging to make them with very controllable size and very nice size distribution. In fact, most of the optical and electronic properties which I will be talking about, they require in fact very, very narrow size distribution. And well, in fact, what is required is a mono size distribution that you don't, the best will be that there's no distribution, but that's extremely difficult to get in practice. So it's extremely, from electronic and optical point of view, it's extremely important to synthesize these materials with controllable size. So the synthesis technique should be such that you should be able to vary size over a very large size range and control the size distribution. So we will move from size-selected nanoparticles to single and in some case pair nanoparticles. Pair nanoparticles will be important. You will see that when I discuss it, that maybe we would like to, for certain application, we would like to make pair of particles, one nanoparticle maybe of a rare earth material and another particle of palladium, and we want to attach them together. So so you can see that starting from thin films, nanocrystalline films, then size-selected nanoparticles controlling their size distribution, and then moving on to single and pair nanoparticles. This is how so when you are going, it's some sort of a advancement in the synthesis technique, improvement in the performance of the device, but it becomes very challenging and difficult tasks, and that's what I'm going to demonstrate this in this talk. Similar thing in case of oxide, and this is now a separate class of, it's not related to the first one. So these oxide materials are very well-known materials for very large number of applications. They can be used, but one of the application is making resistive memory devices based on the oxide materials. And these resistive memory devices, in fact, at present, are being made from using thin films of these materials and then using photolithography techniques and controlling their dimension and reducing their dimension. What we have shown is, in fact, in our group, we have used first time a nanodot structure and made resistive memory devices and showed that the resistive switching phenomena is possible you can use nanodot structure, and there are a lot of advantages. And I will be showing them in this talk that what are the different advantages if we move on from thin films to nanodot structure. And this is some sort of our future goal, that if it will be possible to make a device using a single nanodot, and then ultimately it is possible to make very high density devices using this kind of approach. So that's my objective of my goal, objective of the talk. This is the first material which I was discussing, rare earth materials. So looking at the audience, having diverse background and many students sitting in the audience, I'd like to give a brief introduction about how does hydrogen interacts with the rare earth material. Okay, this is nothing to do with nanoparticles or thin films. This is how hydrogen interacts with a rare earth material in bulk form. Okay, and there are a large number of applications of these materials, and I will be picking up one application, and that application that is called switchable mirror application. So in the switchable mirror application, the conventional structure of the switchable mirror device is something like this. You have a substrate. For all thin film applications, you require a substrate because they're not mechanically strong. So there's a substrate, and you have a rare earth thin film. And in this case, we have chosen the example of gadolinium. We have worked with gadolinium, praseodymium, yttrium, large number of rare earth materials, but in this talk I will be taking the example of gadolinium or praseodymium also. And so you have a thin film of gadolinium which is covered with a palladium overlay. When this structure now interacts with hydrogen, gadolinium, it's in the metallic state. It's a metal. It goes to what is called a gadolinium dihydride phase. Each atom of gadolinium gets attached to 2 atoms of hydrogen. And when it goes from metallic, still it is metallic, but there is a change in the color. Gadolinium dihydride is blue in the reflection mode. If you see this material in the reflector light, it will appear to be blue, but you can see that there is a crystal structure transformation. The material has already changed its crystal structure. In rare earth metal of gadolinium was SCP hexagonal close-packed crystal structure. Gadolinium dihydride is FCC, face-centered cubic. You put more hydrogen, it goes to another phase of gadolinium trihydride, GDH3. It has become now metal to semiconductor. The material has changed its nature. In dihydride, this phase is normally called a dihydride phase. The dihydride phase was metallic, so it has a blue in the reflection mode because that's what matters. Their color is decided what they appear in the reflection. Semiconductor, it's yellow in the transmission light because it has a band gap, so the light gets transmitted. Depending upon the band gap of gadolinium trihydride, the color will be decided. So what is interesting is that there is a crystal structure has changed and we go from metal to dihydride to trihydride. The nature of the electrical nature of the material has changed. It was metallic, it has become semiconductor or insulator. Optically, it has changed. It was reflecting, here it has become transparent. Interesting thing is you can go back and forth. You can go from dihydride to trihydride. When you remove hydrogen, the material comes back to dihydride state. And reversibly, you can go back and forth. You cannot come back to the metallic state, but you can come back reversibly to dihydride state. And you put more hydrogen, again you can go back to the trihydride. So this is a reversible transformation. But there are 2 or 3 types of transformation taking place together. There is a crystal structure transformation, there is a metal to insulator transformation, and the material is changing its optical nature. You can see that it's very remarkable. Another interesting thing is this is taking place at room temperature. This is very important from device point of view. You don't have to operate this device at higher temperature. You don't have to go to higher temperature to remove hydrogen, for example. It's also interesting from hydrogen as a hydrogen material. From solid state physics and chemistry point of view, this is an extremely interesting system in the sense that this is a unique system that you can put 300% of one element in another element. When you go from gadolinium to gadolinium hydride, you are putting 300% of hydrogen into gadolinium, and you can remove 1/3 of it. Okay? And how does this transformation is taking place at room temperature? This is also it's not very well understood. This effect was first time reported something like 6 to 7 years back, and a lot of theoretical and experimental investigations are going on to understand how metal to insulator transformation and how crystal structure transformations are taking place. Another very interesting and complicated issue is that these 2 transformations are not related to each other. The metal to insulator transformation has nothing to do, the crystal structure transformation is taking place because there are rare earth materials like praseodymium I mentioned. In praseodymium, there is no crystal structure transformation. The material remains in FCC structure, but there is a metal to insulator transformation. Optically, the material is changing, electrically, material is changing, crystal structure remains same. So they cannot be related to each other, but they are independently taking place. So it's very interesting material to study from solid state physics and chemistry point of view. Another interesting thing is that we require a palladium overlay because this is very important from what we are going to discuss. These materials are highly susceptible to oxidation. The moment you expose rare earth material to oxygen, it immediately gets converted to oxide. That is why we require a palladium overlay. Palladium protects the rare earth material from oxidation. So it's a protective coating of palladium. Palladium also plays very important role, what is called dissociative absorption. When the hydrogen is going into the rare earth material, molecule of hydrogen is converted to atomic hydrogen. There's a catalytic reaction takes place at the palladium, And it is the atomic hydrogen which then interacts with the rare earth material when the hydrogen is going in. During this process, from dihydrate to trihydrate, when the hydrogen is coming back, again, two atoms of hydrogen must come together at palladium site. It is not that they can just come together anywhere and molecule of hydrogen can be formed. It does not happen. The catalytic reaction has to take place. Two atoms of hydrogen has to come together at palladium site, and then molecule of hydrogen is formed, and what comes out is molecule of hydrogen. So palladium plays important role during what is called dissociative absorption when the hydrogen is going in, and associative absorption when hydrogen is coming out during loading or during deloading. So I was mentioning that we are studying this for switchable mirror application, but there are a large number of applications you can see: solid state displays, optical windows, sensors, hydrogen storage. This is what happens actually. You can see that as a function of time, electrical resistance. Electrical resistance of the metallic state, dihydrate state, but when you go from dihydrate to trihydrate, you can see there is a large increase in the electrical resistance. The material has gone from metal to insulator or metal to semiconductor state. If you look at the transmission, in the metallic state it's reflecting, so the transmission is very negligible or very small. When it goes to the trihydrate state, the transmission is very large. So there is the optical transformation and electrical transformation at this point, and this change in the electrical and optical properties at room temperature has been used or is being used for a large number of these applications. I mentioned that this first time it was observed something like 5 to 6 years back, this effect in rare earth materials, and since then, because of large scope of the applications, because different applications, different material systems have been tried out, and the objective of using different material system for this purpose was to improve these properties. These are the properties which are useful for or required for switchable mirror application and many other applications. Color neutral transparent state. In the trihydrate state I mentioned, gadolinium trihydrate is yellow in color. You don't want your window to be yellow in color if it has to be used as a smart window material. You want the window to be, when the material is in the transparent state, we want the transparent state to be color neutral. The transmission should be same at all wavelengths of light, at least in the visible part of the spectrum. So the color neutral transparent state, faster response time, large change in the optical properties, stability towards oxidation, I already mentioned it's a very big problem, and reversibility. To improve these properties, people have used, work started with rare earth materials, then people started mixing magnesium with rare earth material, because magnesium also interacts with hydrogen, and it also has similar properties. So they try to make alloys of rare earth materials with magnesium and tried investigating these properties. Then some people also make multi-layer structures, gadolinium, magnesium, 30 layers, each layer having 100 angstrom thickness, and they made multi-layer structure, and they try to investigate the switchable mirror effect and interaction of the multi-layer structure with hydrogen. And what was found is that in case of alloy, there's only improvement in the color neutral transparent state, all the other parameters get affected in the reversely. When you go to multi-layer structure, there's improvement in the response time, color neutral, optical contrast, stability, oxidation, everything deteriorates, is affected in the adverse direction. Around 3 to 4 years back, we thought of using nanoparticles based switchable mirror, rare earth nanoparticles for, and our idea was there are 3 reasons why we thought we should make switchable mirror based on rare earth nanoparticles. Blue shift, all of us know, blue shift due to quantum confinement effect. When you have semiconductor material, as you know that the trihydrate state is semiconducting state. In the semiconductor, if you have nanoparticles and you confine the electrode to small dimension, there is an increase in the band gap of the semiconductor. And that yellow color was due to the band gap of the gadolinium trihydrate. And if we can make nanoparticles of gadolinium, on interaction it goes to gadolinium trihydrate, which is a semiconductor, and you have small dimension, you can push this band gap towards the blue and make all the energies below the blue light will be transmission, So it's possible to get color neutral state without changing the chemistry. You can see that what is being done here is you're putting another material, and that it's modifying the chemical reaction of this material with hydrogen. You make nanoparticles of this material, and it should be able to, one should be able to have color neutral transparent state, or the color neutrality can be improved. Enhanced surface area. As you go to smaller dimensions, there is an increase in the specific area. The surface area per unit volume of the nanoparticles is much larger, and this magnitude becomes larger as we go to smaller dimensions. And as the surface, because this reaction with the hydrogen is taking place because of the surface area, and is taking place at the surface of the material, we expected that when we go to make nanoparticles of these materials and use it for switchable mirror application, there will be an obvious enhancement in the switchable mirror properties of these materials. The only thing which we were not sure was that many times in solid state materials, when you go to smaller dimension, there is a modification in the crystal structure, which is called the size-induced structural transformation. Because of different reasons, the crystal structure of the material in the bulk form and in the nanoparticle form can get changed. What will be the effect of that change in the crystal structure due to the size on its interaction with hydrogen? We were not very clear. But the first two effects, we were very sure that that will result into the improvement in all these switchable mirror properties. So I'm very happy to tell you that we were in fact the first group to use nanoparticles of rare earth materials for this particular application. In fact, we were the first group to synthesize nanoparticles of rare earth material, because it's extremely difficult because of their oxidizing nature. They oxidize very quickly. So that is what I'm going to describe how we do it. And but before that, let me tell you that we investigated three systems when we were doing that. The first system is a simple structure of what I described earlier, that you have a thin film of rare earth material which is protected by a palladium overlayer. The only thing which we changed was that we modified the thin film of rare earth material, and we used a very extremely simple technique which I will describe later, and changed the thin film to a nanocrystalline layer. Okay? And in the nanocrystalline layer, and we kept the overlayer, palladium overlayer, as it is. And what we found was that there is a comprehensive improvement in all the switchable mirror parameters which I described. All of them improved. What we did, we just made a small modification in our synthesis, and there was a tremendous improvement in all these switchable mirror parameters. And this is why in fact, it's a very good example to show it to the student, that many times when you go from thin films or bulk materials to the nanoparticles, there can be some advantages and there can be some disadvantages in properties and in application. But this was some sort of we were fortunate to have this kind of problem, that all the properties of the device improved as we go from thin film or bulk to nanoparticles. The second system which we try to investigate, as I already mentioned, rare earth materials are highly susceptible to oxidation. If thin film reacts with oxygen very quickly, nanoparticles will react even faster. Just like we expect the nanoparticles to react faster with hydrogen, we should also expect nanoparticles will react with oxygen also more. So we were very much concerned about the stability of rare earth nanoparticles in oxygen. So we wanted to investigate that what happens when you go from thin films to nanoparticles. Let's expose these particles to oxygen. So we removed, what we did, we removed the palladium cover. We exposed these nanoparticles to oxygen and then investigated the properties. And to our surprise, these nanoparticles were stable in oxygen. At least their stability was much better in comparison to thin films and bulk materials. So this was a very, very surprising result. But now we understand it, that why it is happening. Then the third system which we investigated was that because palladium also is very important, as I already mentioned, palladium is playing the role of a catalytic, and catalytic reaction takes place at the surface. We thought it's obvious that we should modify, we should change the palladium overlayer and bring palladium nanocrystalline layer. So increase the surface area, increase the catalytic reaction. So to investigate that effect, we kept the rare earth material as a thin film and made the palladium overlayer as a nanocrystalline layer, and we observed that there is a large improvement in the recovery. Recovery time I will describe later. Whenever your hydrogen is going in, it goes very fast, but the hydrogen removal is very slow. This is true for all sensors on all kind of materials which interact with gases. Because it is also very easy to understand that when hydrogen molecule is going, it is going at one palladium site and getting converted to 2 atoms of hydrogen. But when the hydrogen has to come, or 2 atoms have to come together at a particular site, combine together, and so thermodynamically and also kinetically it's a slow reaction. So the recovery times are always slower than the response time. And in this case, we could find out, it was very nice to observe that the recovery time can be improved by making the palladium, changing the palladium thin films to palladium nanoparticles. And you can see that all the results are very dramatic. And all these, work of this is a work of something like 3 or 4 PhD students, so I'm not going to describe that here. But, and this is given in this is a 200-page book chapter we have written on Handbook of Physics and Chemistry of Rare Earth Metals, Rare Earth Switchable Mirror. So all the results are described there. So what I'm going to do now is, I'm going to give you just maybe 1 or 2 results of which are more important results, or more dramatic, and then move on to the next step. This is what I meant by, see, you are in the metallic state. This is, in fact, you can see that this is in case of praseodymium. There is another kind of rare earth material. There is a metallic state, electrical resistivity. When you expose it to hydrogen, the electrical resistance goes faster. It goes to correspond to trihydride. When you remove it from hydrogen atmosphere, it comes back, and you can see that you are not coming back to this state, but you're somewhere in between. And you can go back and forth. This is what, and this is, and you can see that this is in case of thin film, and this is in case of nanoparticle. This is the comparison. You can see the yellow curve. In case of the nanoparticle, the electrical change is something like twice that of a thin film. And you can also calculate the response time. In case of thin film, the response time is around 150 seconds, and in case of the nanoparticle, it's around 94 seconds. Similarly, there is a change in the optical properties. You can see that this is the transmission in the material, metal, dihydride, and trihydride. And you can see that this is the optical contrast in thin film. And in case of the nanoparticle, you can see the optical contrast shown by that green arrow has increased. Similarly, this is the color neutral transparent state compared for gadolinium nanoparticles, gadolinium magnesium alloys, multilayer, and polycrystalline. So there's a improvement in the color neutrality, and we can prove that that's actually due to the shift in the absorption edge of the nanoparticle trihydride state due to the reduction in the size. Okay, but before I go further, let me tell you that how we were making this nanocrystalline layer. You must have noticed that while describing the results, I only compared thin films with nanocrystalline layer. I did not change the crystallite size, because in our technique it was not possible to change the crystallite size. Thin films were being prepared by a vacuum evaporation setup, and what we did, we created the vacuum, and then we introduced an inert gas, and this is called an inert gas evaporation method. This is a very simple method. Because of the incoming vapors, when they come and get deposited, they collide with the argon gas inert gas atoms, they lose their energy, and when they reach the substrate, they cannot move on the substrate with high kinetic energy, so that results into small crystallite size. The problem in this technique is that the size distribution is very broad. You have particles of all sizes present there. So we can only compare a thin film with a nanocrystalline or a polycrystalline layer, with a crystallite size, average crystallite size is something like 20 or 18 nanometer, but we cannot change the crystallite size. This is what I was mentioning, that this is extremely important. If you want to understand how these parameters change with crystallite size, we must have first a synthesis technique, where it should be possible to change the crystallite size in a controllable fashion, keeping the size distribution narrow. So this was one of the problems in the initial state. So this is another experiment we did, that we wanted to investigate what is this improvement which is coming due to. So this is a experiment done using a technique called elastic recoil detection analysis. This is a technique where you can measure the hydrogen concentration in the material and also the hydrogen concentration profile in the material. And you can see that in case of a, we can see here, this is the, in case of nanoparticle layer, this is the loaded state and this is the deloaded state. And this dashed area shows that how much hydrogen you can remove when you go from trihydrate state to the dihydrate state. And you can see that in case of nanoparticle, there is a large amount of hydrogen you can remove, and this hydrogen is present throughout the thickness of the material. Whereas in case of the thin film, the hydrogen is only present at the top surface, which is in between palladium, catalytic layer, and thin film. And the amount of hydrogen present is small. So all the changes which we are observing, the improvement, is actually due to that we are able to put more amount of hydrogen, and also we are able to remove more hydrogen. The two things are important, that you should be able to put more hydrogen, and more hydrogen should be able to, one should be able to remove. This is the second system which I was mentioning, that we just put palladium in the second system. We only have a underlying thin film, and we removed the palladium thin film and made palladium nanocrystalline layer. And you can see that this is what I was mentioning. This is the switching time. In the red curve, if you follow the red curve, the switching time is very fast, and the material comes back to its normal state also very fast. If you look at a blue curve, it's going very slowly, and also it is coming out very slowly. So this part is switching, this part is recovery. And it is shown here that how recovery and response and recovery time changes as a function of average crystallite size. This is very important. But then we moved. Now, this is the fourth system which we wanted to investigate. Now we wanted to investigate directly, because we have seen that when we change palladium thin films to palladium nanoparticles, there is a large improvement. So we directly wanted to investigate their effect. So in this case, we studied three systems. The first system is palladium thin films and palladium nanocrystalline layers formed by inert gas evaporation method, which I mentioned earlier. And then the third system is based on size-selected palladium nanoparticles, where it is possible to make nanoparticles of very well-controlled size. This is, in fact, this is the method I was mentioning earlier. You use vacuum evaporation to make thin films. You make nanocrystalline or nanoparticle layers using inert gas evaporation method. Inert gas evaporation method, when the atom reach the substrate, they have lost their energy by colliding with the inert gas atom. So they have less energy, and that results into smaller crystallite size. But the crystallite size, smaller particle size, but there is a loose and slack topography. In thin films, you have well-corrected crystallite, and the crystallite size is large. This is also going to be slightly important. This is, you can see that the moment we change the palladium thin film, this is how a palladium thin film interacts with hydrogen gas. You have, this is what I'm showing is the electrical resistance of the palladium film. You have a palladium film, you put two electrodes, measure the resistance, expose it to hydrogen, and this is the resistance corresponding to palladium when there was no hydrogen. As the material is exposed to hydrogen, the resistance starts increasing slowly. We call it a slowly increasing or slow saturate. It slowly increases and then saturates. And when you remove it from hydrogen, it comes back. What has happened is, in thin films it was like this. When we have nanoparticles, you can see that the resistance is suddenly going up, and you can also see that it's slowly coming down. Here, it's even going faster, and you can see that the amount of decrease is also very large. So in this case, you can see that what has happened is, compare this case, first case, with this case. In the first case, as the palladium is exposed to hydrogen, it slowly resistance increases and saturates. In this case, you have the electrical resistance, it goes up and comes down immediately. Still the material is exposed to hydrogen. At this point, you remove the hydrogen. The resistance again goes up and again comes down. There is a dramatic effect. You can see that how palladium thin film is responding to hydrogen, and how a palladium nanocrystalline layer is responding to hydrogen is totally different. And the only thing which we have done is, in place of the vacuum, we have introduced an inert gas. So these crystallites are around, they were deposited at 250 degrees centigrade. You can see they're large crystallites, and we expect them to be connected to each other because they're grown at high temperature. These are small crystallites, and they are grown at room temperature, so they have some loose topography, and later on we will explain this, why it's happening. This is the method which we are using to make size selected nanoparticles. It's a very interesting method. So it has in fact 3 or 4 steps. In the first step, what we have is, it's a spark generator method. It's called spark generator. This is nothing, we just want to evaporate the material. We have palladium in the bulk form, we have wires of palladium or rods of palladium, 2 rods of palladium, there's a spark generator between them. And the spark erodes the palladium metal, and the palladium atoms goes into the vapor phase. Some sort of a heating or sputtering, and that kind of process takes place. As the palladium atom goes to the vapor phase, this A and B is the inert gas, the nitrogen takes these atoms in this pipeline. And as the atoms are moving in the inert gas, they are colliding with each other, and they are forming, you can see that, different types of agglomerates. These agglomerates have different sizes and different shapes. This is what you normally deposit. When you people make these nanocrystalline layer, the nanocrystalline layer can have agglomerates of different shapes and different sizes. No control on the size. You can change the average size of these agglomerates by changing the flow conditions. But there is always going to be a very broad distribution. I will show you the distribution at this stage. What we do now is, we pass these agglomerates, the gas carries these agglomerates through a UV charger, where these agglomerates are positively or negatively charged. Gas containing the charged agglomerates passes through another device which is called differential mobility analyzer. In the differential mobility analyzer, you have 2 electrodes, there's a central electrode and there's an outer electrode, there's an electric field between them, and the differential mobility analyzer selects the particles of one charge. You can see that if the central electrode is negative, only positive charged particles will go towards it, and they will be removed from the remaining stream. And what you can see here you have different shaped and different sized positively and negatively charged particles. What is coming out is only positively charged particle because the central electrode was negative. If we keep the central electrode positive, we can take out negatively charged particle. This is also interesting. Later on I will show you why it is useful. So what is coming out here is positively charged particles. So gas takes these positively charged particles through a sinting furnace, where these particles now are taken to very high temperature close to their melting points, where these particles now, these agglomerates now, they will melt, and when they melt, they are still in the gas, there is no substrate, they will form spherical droplets. And as they come out, they slowly cool down and transform the liquid, or near almost liquid-like phase is transformed to a solid particles. And you can see that we have selected particles of one size, we have made them spherical, we have made them crystalline. This is also very important. And then we deposit, the gas takes these particles to the deposition chamber where these can be deposited on wherever you want to deposit this. Something like this. This is the experimental setup. You can see that this is the spark generator. The particles comes through this pipe. This is the charger here. The tube takes the particles down. This is the differential mobility analyzer. It selects the size. Then they go through the sintering furnace. They enter here and they come out here, and here they get deposit on the chamber. And this is some sort of a computer which controls the deposition process. And how the deposition process, in fact, this is how the differential mobility analyzer works. You can see that I was mentioning there is an inner electrode and there is an outer cylinder. You have electric field between them. If you have positively charged positive electric voltage applied to this central electrode, then the negatively charged particles will go in this direction, and there will be 2 forces, one due to the electric field, because the charged particles, they will be attracted towards one direction, because so there is the electric field and there is a drag force, because as the particle gets accelerated, they are moving in the gas, there is a viscosity, the gas will retard their motion, and after some time they will get a terminal velocity. So they move, so depending upon their mobility in the gas, depending upon how much gas retards the motion of the particles, particles of a particular mobility enters this point, particles having smaller mobility are deposited on the substrate, particles having larger mobility go out in the exit, and you select particles of a particular size. This is important. You can see here. The red curve is something if we had deposited particles without any size selection. This is number of particles as a function of size. You can see that the broad size distribution starting with around 15 to around 19 nanometer. All kind of particles are there. The average size may be around 40 or 50 nanometer. If we selected the particles, what we are doing is we are selecting particles which are following this blue line. So you're selecting, although you're selecting a small number of particles, but all these particles are having the same size. If we want to look at, if you go into the transmission electron microscope, this is what is happening. This was the agglomerates of different sizes and different shapes. This is, they're taken through the sintering furnace at different temperatures of the sintering furnace. You can see that at 400 degrees centigrade, already the compaction has started taking place. The particle which are having a loose structure and arbitrary shape, the particles, because they melt, they start coming together. Process of compaction starts. After the compaction has taken place, then if you increase the temperature further, they will melt and they will form bigger spherical particles. If you look into the transmission electron microscope, you can see that by giving a different voltage to the differential mobility analyzer, you can select particles of different size, 6 nanometer, 11.2 nanometer, 15.3 nanometer. You can measure their size distribution, and the size distribution in this case, geometric standard deviation is less than 1.04. Mono size distribution, they have geometric standard deviation of 1. Very close to a mono size distribution. You can see, if you go to the high resolution transmission electron microscope picture, you can see the lattice imaging and the monocrystalline. They're monocrystalline, they're spherical, they're monocyte. Now, if you use this kind of technique, then now it is easy for us to understand that how the interaction of hydrogen with palladium or with rare earth material takes place as a function of size, and we can investigate this as a function of size. So then we started investigating. Remember, I mentioned two kind of effects: slow saturation and pulse-like, where the resistance goes up and comes down. What we observe now is that the pulse-like response, which I was mentioning, and the saturated response, it is a function of hydrogen concentration, it is a function of the measurement temperature, and it is a function of the nanoparticle size. In fact, there are a large number of processes taking place when the hydrogen is interacting with the palladium. What we are observing is there is a simple increase in the resistance, but that increase in the resistance is taking place because of 2 or 3 physical processes which are taking place. And these physical processes, they change. What are these physical processes? There is adsorption of hydrogen. First molecule of the hydrogen has to go and get attached physically to the palladium surface. Then chemically it has to get converted to, from hydrogen molecule gets converted to, chemisorption takes place, gets converted to atomic hydrogen. Then this atomic hydrogen diffuses into the palladium structure, gets incorporated in the palladium structure. When palladium goes from palladium to palladium hydride, there is a 4% lattice expansion takes place. The nanoparticle will expand. This palladium also acts like impurity scattering centers. So there is a crystal structure is expanding. The electrical resistance, because of scattering effect, the electrical resistance, the mobility gets affected. So physical adsorption, chemical adsorption, diffusion, incorporation into the lattice, expansion of the lattice, and change in the electrical properties. So all these processes, they decide whether you will have a pulse-like response or you will have a saturated response. Okay, and we did a lot of, and as you can see here, at 5% hydrogen, at 20 degrees centigrade, you have a pulse-like response. At 0.5% hydrogen, you have a saturated response. Same thing happens with temperature. If the temperature is 80 degrees centigrade, at all hydrogen concentration, you have a simple saturated response. If the temperature is 20 degrees centigrade, below 2.5, a slow saturation response. Above 2.5, it is 5% saturation response. Okay, so I think I will skip this. What this is happening is there are in fact 2 important effects which takes place. This is the pulse response. This is actually a superposition of 2 effects. One is the electronic effect. Electronic effect is hydrogen acting like scattering centers in palladium. They scatter electrons and increases the resistance. So the resistance increases. When the slow saturation response is there, that means this effect is dominating. Geometric response is there when you have 2 palladium nanoparticles together. hydrogen goes into them, they expand, they come closer to each other, they start touching each other, and because they touch each other now, their electrical resistance decreases. Because the barrier for electron to go from one particle to other particle is reduced, and hence now, so this effect, there is an increase in the electrical resistance, and this effect, there is a decrease in the electrical resistance. Depending upon the response time of these two effects and their magnitude, you can have a slow saturation response, or one can have a pulse response, depending upon that. I think I will not go into the detail, but what is important is that we can find out there is a threshold concentration at any temperature below which the response is slow saturation, and this threshold concentration depends upon the temperature. So depending upon what concentration of hydrogen one wants to measure, you can keep the sensor at a particular temperature and measure the threshold, measure the response, and you can in fact detect not only hydrogen but also the concentration of hydrogen. You can get an idea what is the concentration of hydrogen. For example, if the temperature, measurement temperature is 40 degrees centigrade at 4% hydrogen, the response changes from slow saturation to pulse like. So you can measure 4% hydrogen, you know, is very important because it's the explosive limit for hydrogen. So that kind of sensor can be made. This is another extension of the same synthesis setup which we are doing presently. What I mentioned earlier, this is the evaporation furnace or a spark generator. Then we had a charger, we have a DMA, sintering furnace, and positively charged particle, let's say. We keep the central electrode positive, the nanoparticles which will come out will be negatively charged. So you have material A, negatively charged particles comes out and they go into this tube. This electrode here, DMA, the central electrode is kept negative. Here you have material B, what will come out will be positively charged particles. These positively charged and negatively charged A and B particles are flown through this coagulation furnace where they again collide with each other. So positively charged particles and negatively charged particles will come together, and then we filter them because some of them have not collided, they will have a charge. Those charged particles are removed. The only particles which are allowed to enter, go in this direction are the particles which are neutral. That means the particles which are neutral must be the particles which are in pairs. And then you can also again select them according to their size, because you know the size of A, you know the size of the B, and you only allow the particles which have size A plus B or mobility corresponding to A plus B, and then you deposit them. This way, this is one of the methods by which we hope that we will be able to make pair nanoparticles. And why we are interested in making pair? This is an example of pair nanoparticles of silver and palladium sulfide. You can see that as you go to the high resolution transmission electron microscopy picture, you have a silver particle and you have a palladium sulfide nanoparticle, and you can control their sizes independently and then attach them. Why we are interested for this application is we want to make this kind of device. You have a gadolinium rare earth nanoparticle and you attach with it a palladium nanoparticle. And what will happen is now the hydrogen atoms comes, it goes to the palladium, there it gets converted to atomic hydrogen, and this atomic hydrogen then goes into rare earth material, changes it from rare earth to rare earth dihydride or trihydride. There is a change in the optical properties and electrical properties of the nanoparticles, and if you can detect that, this will be a 1 nanoparticle or 2 nanoparticle based device. Okay. The advantage is, I did not mention, when you go from thin films to polycrystalline to size selected nanoparticles, what is happening is there are other important parameters also. One of them is hysteresis. When the electrical change in the electrical properties or optical properties as a function of increase of hydrogen concentration and decrease in the hydrogen concentration. When you go through the complete cycle, there should not be any hysteresis. When we have a single nanoparticle, the hysteresis is coming out because of the interaction between each particle, which are, and they are, because you have one particle and there are other particles present along the way, they do not allow the particle to expand and contract. And that is one of the reasons for hysteresis. If you have an independent particle, it is interacting with hydrogen and you can measure its electrical properties, it should be able to make a single particle or pair nanoparticle, single nanoparticle space. That's what our present research goal. So here I will switch the change the gear and go to, yes. What happens is that under certain conditions, you can change the electrical resistance of the insulating material. And how it can be done is something like this. This is the initial electrical resistance. When you apply a particular voltage, at this voltage, the electrical resistance becomes very small. This is called the first process of electroforming of the random access memory. The material goes to what is called a low resistance state or state 1. If you measure the IV characteristics, you vary the voltage, you will be along this path. At this voltage, which is called the reset voltage, the device again goes back to the high resistance state. And so you are switched from state 1 to state 0. If you apply this voltage, which is called the set voltage, the device again goes back to state 1. So by applying certain magnitude of the voltage, you can switch the device from 0 to 1 state reversibly. And this is one of the methods of using. There are resistive memory devices, there are capacitive memory devices, you must be knowing. The resistive memory devices, the advantage is a very simple structure. So the cost is very low, they can be scaled up, the possibility of scaling up is very high. You can have large number of devices because of the nature. You can have large number of devices per centimeter square. So this is, in fact, there are different mechanisms, but one of the mechanisms which I'm going to describe is something like this is the initial state. There's nothing happened. You make the device first. You are forming the device. What you are doing is you apply a very high voltage. There's some sort of a soft breakdown of the dielectric material takes place, and what you have is you form a conducting filament. The dimension of this filament are in the nanometer range or micron range. What you have done is you have made some sort of a micro or a fuse, electrical fuse at a nanoscale by applying this forming voltage, by applying a very high initial voltage. At the reset, what you're doing is you're applying a voltage, you're increasing it so that very high current starts flowing through the filament and the filament breaks down partially. And so this filament breaks down, device again goes back to high resistance state, off state, 0 state. You again apply voltage so that that forming again takes place. But now because already the filament is there, you don't have to go to that forming voltages, you don't have to go to very high voltage, you can work with smaller voltage. So that is called the reset voltage. So you can go, this is one sort of mechanism. There are other mechanisms also with people. In different materials, there are different types of mechanisms. One of the material where there is a copper oxide in which I will be describing, that is the filamentary method, filamentary mechanism. This is how the current voltage characteristic, which in fact I have already described. This is the structure. I think we can skip this. This is, we were using a thin film, but now what we were doing in the thin film, which I already showed you, that you form a filament, and the switching depends upon the filament, formation of the filament. What is important is when you go from one cell to another cell, there should be uniformity in the switching parameter. That means the resistance in the on state, resistance in the off state of all these cells should be same. It depends upon the uniformity in the properties of the material. It depends upon the uniformity of the filamentary formation process, which cannot be uniform because it is statistical. Because it's taking place randomly. You're applying a very high voltage and the dielectric is breaking down along the grain boundaries, along defects, along voids. That copper is diffusing and forming a filament. Its shape and size is not very well defined. What we thought that we should use nanorods. So these are copper oxide nanorods made by what is called a template assist deposition method, which we're discussing during lunchtime. You have a alumina template. To the template, you electrode deposit, and then you remove the template, and what comes out is you can see these are copper oxide nanorods. Their dimensions are around, this one is around 90 nanometer, but it's possible to go from 30 nanometer to 90 nanometer by this method. But what is possible is that you can have really standing nanorod structure. So what we did, we had this kind of structure, then we made a insulating material, then we opened it, filled the mercury, and had an electrical contact. And you can see that we could observe electroforming process. This is the first step. You apply this voltage around 11 volts, the material goes to the low resistance state. And then you can see here, You are in the low resistance state, at this voltage it comes back to the high resistance state. At this voltage it goes back to the low resistance state. So you can go from the low resistance state to the high resistance state by applying the voltage. Using copper oxide, not using copper oxide thin film, but using copper oxide nanorod, it was possible. We did some, this is a composition of one copper oxide nanorod before forming and after forming. We measured the copper concentration of copper as a function of, with respect to oxygen. And you can see that in the electroforming nanorod, we could see that the copper concentration at certain points becomes very high. That is indicating that in that 100 nanometer dimension, at certain points, there is some formation of copper filament. What we think is, what is the advantage of using copper oxide nanorod in place of copper oxide thin film? That the filamentary, each nanorod, in fact, each nanorod is acting independently. So what we have is, we don't have a thin film now, but you have a parallel network of the copper oxide nanorod. Each nanorod, because it's isolated from the other electrically, there's a gap between them, and also on the surface of the nanorod, copper oxide nanorod, there's some alumina template. Always you can keep the etching condition such that some alumina always remains on the surface of the copper oxide nanorod, so that they electrically they are not touching each other. So each nanorod acts like a simple switchable resistor. What you have, if you have 1 micron scale cell area, you will have n number of these resistors in parallel. The dimension of each resistor is fixed. It is possible when you forming the span, the dimension, the lateral and longitudinal dimension of the copper filament will be confined to the dimension of the nanorod. And hence it will be possible to go, when you change the cell area, your response is not changing. And you will further, if you can have this kind of device and you can make two electrical connection to single nanorod, it's also possible to make a switchable device using one single nanorod. And it's possible to do this kind of thing, is also possible to do today using focused ion beam and this kind of technologies. And this is another research direction in which we are working today. So thank you very much.